Hello everyone, I'm Melissa, an onboarding engineer at SkyCiv. Welcome back to our series on the ADM 2020 Aluminum Member Design Calculator. In my previous videos, I walked through this calculator's features and functionalities, as well as a deep dive into the axial compression checks it performs. Today, I will walk you through this design example. I have my design example side by side with my calculator, so let's get started. The design example says given aluminum association standard W shape AW 8 by 6.18. The quick design calculator has the ability to create custom sections where you can edit the section dimension, or you can add sections from our database. That's what I'm going to do here. Right now I have hollow rectangular selected, so I'm going to select I section, and then I will select an 8 by 6.18 section. The section dimensions are now grayed out since we're using a section from the database. There's no mentions of this being welded. The alloy is 6061 and the temper is T6. And the product specification is B308. Those are our section properties. And now we have a length of 8 feet. I'm going to change this to 96 inches. And now we need to find the major axis bending capacity. This design example doesn't give any design loads. It's just asking us to find the capacity. I'll just enter 0 for these design loads for now. Now I'll run the calculator. I downloaded a PDF of my report by selecting this button, so let's open up my report in a different tab to take a closer look. SkyCiv gives a comprehensive calculation report for each of the quick design calculations. This is just a summary of the inputs we entered and our section profile, as well as our section properties that are calculated based on our section profile. These are our material properties based on the material inputs we entered in. You can see the exact section of the code these calculations reference in the left-hand column. Now let's walk through how the major axis bending capacity is calculated for the section using the ADM 2020 Aluminum Member Design Calculator. This part of the report demonstrates how the tool evaluates the section's ability to resist bending moments about its major axis while ensuring compliance with the code. The tool uses the input parameters that define the section's geometry and material properties. Additionally, it considers user-defined bending moments for both major and minor axes. In this case, the major axis bending moment is input as 0 kip inch. We'll focus on determining the capacity of the section rather than its utilization. The tool evaluates 2 critical checks: yielding. It calculates the moment capacity based on the plastic section modulus and material yield strength using this equation. Here, ZZ is the plastic section modulus, SZ is the elastic section modulus. Based on these values, the yielding moment capacity is determined. The rupture capacity is calculated using the ultimate strength of the material. For this section, the rupture capacity is 321.538 kip inches. Once both yielding and rupture capacities are evaluated, the calculator determines the governing capacity as the lower of the two. In this case, it's the rupture capacity as 321.538 kip inches. This value represents the section's major axis bending capacity. Moving on to the local buckling check, the tool then checks for local buckling of the flanges and web using slenderness ratios and weighted average methods. You can also opt to have this section calculated using limited element. This is in the calc settings portion of the input. If you hover here, you can read the method used for calculation of local buckling and bending. So we have the weighted average method selected, meaning the capacity is based on the weighted average capacity of each individual element across the entire section. Back to the report. For the flange, the slenderness value is calculated as lambda equals b over t, comparing this slenderness value to the code defined limits ensures no local buckling occurs. For the web, the calculator assesses the centroidal effects and determines the buckling resistance of the element. After considering the effects of local buckling, the calculator combines the contributions of the flange and web using the weighted average formula to determine the total fluxural capacity. Here, the calculator produces a final major axis bending capacity of 352.794 kip inches. Utilization ratio is then calculated based on applied loads, which we entered as 0. Another critical check for major axis bending is lateral torsional buckling. This phenomenon occurs when a member subjected to bending about its major axis undergoes a combination of lateral displacement and twisting due to instability. The ADM 2020 aluminum member design calculator evaluates this using the slenderness ratio for lateral torsional buckling. The slenderness value is calculated using this equation where LB is the unbraced length, RYE is the effective radius of gyration, and CB is the bending coefficient. For this section, the slenderness ratio is calculated as 67.908, which exceeds the slenderness limit of 65.673. This indicates the member is in the elastic buckling range. Now we can move on to calculate the capacity for lateral torsional buckling. The lateral torsional buckling moment capacity is determined using the elastic buckling formula, where E is the elastic modulus and SC is the section modulus. Substituting the values, the moment capacity is calculated as 322.081 kip inch. Applying the safety factor of 1.65, the design capacity is 195.2 kip inches. Lateral torsional buckling governs the major axis bending capacity of this section because it produces the lowest capacity compared to the other checks, yielding and rupturing and local buckling. Therefore, the final governing major axis bending capacity for our design example is 195.2 kip inches. This is the answer to our design example question and represents the maximum moment the section can safely resist about its major axis. The ADM 2020 aluminum member design calculator streamlines these complex calculations by automating checks for yielding, rupture, local buckling, and lateral torsional buckling. By providing a transparent and detailed report, it ensures engineers have confidence in their designs. By eliminating the black box effect often associated with design software, SkyCiv ensures you have complete visibility and confidence in every step of the process. Thank you for following along with this example, and we encourage you to explore SkyCiv's tools for your aluminum design projects. If you have any questions about this calculator, remember you can check the documentation here. Also, you can message us with any questions about this calculator or the other SkyCiv software modules. We will answer within 30 minutes. typically. Thank you for following along with this walkthrough and example. Don't forget to explore the ADM 2020 Aluminum Member Design Quick Design Calculator for yourself and see how it can simplify your aluminum member design. Thank you for watching.